Hi everybody. I want to run through these review problems for you so you've got some things to go by before the test tomorrow. Just kind of a starting point. Remember that using Newton's second law, where Newton's second law is that whole F net equals ma situation. So F net equals ma is simply a starting point. It's simply a statement of concepts that says the net force on an object is related to the acceleration of it. But this F net side of the equation is up to you to construct, and you put together the left side of the equation by drawing a free body diagram. So if my water skier is this dot and we're going to be pulled with a force, let's say that this pulling force is to the right, and we can write that as, I don't know, water skiers usually get pulled by ropes, so let's say it's tension. And it says that there is some friction, and that's what we got to figure out. So we'll put friction on there, but we're going to leave it as our unknown. So we can actually kind of put some numbers in there. Sometimes people like to put numbers in there. Here we go again. So if I just try to erase something, sometimes that changes the color choices. Nope. Okay, so the tension is 220 newtons. The friction is the unknown. We've got up and down forces with gravity down, and what do we want to call the force that this surface of the water pushes up with? That's kind of an ambiguous one, so I'm just going to call it force from the water. That's in the upwards direction. And those are equal because there's no up and down acceleration. The forces that belong in this F net equation would be the ones that are, involved with making the motion sideways happen. So let's call to the right positive, and let's call to the left negative, like I usually do. Now when we move that little box, I think I can change colors without changing everything. So these two forces are the ones that make a difference when we're going sideways. So the force from the tension in the rope is in the right hand direction. I'm going to call that positive, and in the negative direction will be the force of friction, and that's equal to the ma. So that's why we use the free body diagram to figure out what goes over here in terms of the forces that affect the sideways motion in this case. So now we can solve it. We can start plugging in numbers. So putting numbers in means tension was 220 newtons, friction is in the negative direction, and that's what we're solving for. That's like our x. The mass of the water skier was 80 kilograms, and the acceleration was 1.8 meters per second. So we need to quick grab a calculator and figure 1.8 times 80 is, and that's 144. So 220 plus negative force of friction equals 144. When we multiply these together, it becomes newtons. Kilograms times meters per second squared is shorthanded and called a newton. That's where the newton comes from. So these were newtons for the tension. The 144 is newtons for the net force, and that net force side is how much bigger the pull is than the friction. And so when we do this math, if we take away 220 and we take away 220, then that's going to be 76 on the right. It's negative 76 because 220 is bigger than 144. And we can cancel the negative signs because they're on both sides of the equation. And what this is saying is the frictional force, the magnitude of it is 76 newtons. And if you were to go back and check, if you put 220 plus negative 76, the negative from that equals 80 times 1.8, they would be equal on both sides, and you did your algebra right, and you did all that kind of stuff. So you guys usually, or should say usually, sometimes want to check your work. That would be how you do it. Just go back and substitute it in, just like you do when you solve an equation for x, and you want to check that. So let's go on to number 2. Car is being slowed down this time. I love everything to go to the right for some reason, maybe because I'm right-handed, I don't know. But the car's going that way and it's slowing down. So if it's slowing down and the forward direction is the positive direction, we'd say that's a positive velocity. So the acceleration we should think of is the opposite direction as the velocity, and that means the acceleration is should be a negative value. And we're going to figure that out up here with these numbers. So anytime you have variables given in terms of speeds changing or distances traveled or times, then that has nothing to do with forces directly. Maybe we need to use that to get to forces. So our free body diagram really isn't going to come into play as far as it did in the last situation, but the force from the brakes would look like this: the gravity force, the normal force. But because we're given kinematic equations, then we're going to use kinematic equations to begin the problem. So first of all, it does say find the net force, and because the only force that affects the motion is this braking force, if we did run to F net equals ma, then it's the braking force equals the mass times A, and we clearly have two unknowns here, and this is where the kinematic equations come into play. So for part A, find the braking force, if we know the acceleration, then 2,000 times the acceleration is the braking force. So the setup in terms of Newton's laws in the free body diagram might get us to the point where we recognize that if I just know A, I can plug that in and I can then solve for part A, the braking force. So if I'm going to go over here and use one of the kinematic equations, I know there's a V final minus V initial over T gives me acceleration. And so V final, be careful of which is which. The final speed is 5 meters per second. The initial speed was 20, and the time it took to slow down was 4 seconds. Always write the left-hand side. Sometimes people start getting rid of that left-hand side just because they're being lazy or hurrying or something, and that leads to problems of not really realizing in the end that you solved for the wrong thing or you used the wrong equation. So the change in speed is in meters per second and the time is in seconds. So if we divide those like we divide the numbers, we'd have 5 minus 20 is minus 15. So minus 15 divided by 4 is not a nice pretty round number, but that's meters per second per second. That is an acceleration unit. And I'll pause for a minute and get that calculation. So that is 3.75. And that's negative. I'm going to make a big ugly negative sign there. So meters per second divided by seconds again in the denominator is meters per second squared, just to kind of tidy up that. So yes, this was a negative sign. I'll make that look a little bit better because that's not super duper clear. Negative. And that goes along with this idea here that the negative acceleration should be what we're looking for in our answer. So now I can change colors. I figured out how to do that. I'm going to change to orange, and I'm going to do orange. I'm going to do part B in orange. How far did the car go in that 4 seconds? So delta X is what we're looking for in part B. So think about the things that are given. I'm going to come over here and I'm going to say we're given V initial equals 20, V final equals 5. We just found the acceleration to be minus 3.75. We want to know what delta X is. So this is for part B. We need an equation that has a delta X in it. The easiest one from the list, and you should always have this list when you're doing these kinds of questions, would to me be delta X equals 1/2 V final plus, this is the only one that has a plus in it. You're used to the ones that are like this, V final minus V initial, sometimes for the deltas, but in this case it is putting them added together, because all this part is doing, this 1/2 and the sum of them, is finding the average value between the final and the beginning, and then it just becomes the average speed times the time. So that's what's going on there, and that's why it's plus. So 1/2 20 plus 5 is, I'm just going to put them together for the sake of space, times 4 for the 4-second time would be, I'm going to say 4 times 25 is 100, times 1/2 is 50. So that's part B. So I know these sometimes get fairly lengthy in terms of the videos. I'm going to make the third solution here a little bit quicker and then stop and end this video, save it, and pick up a part 2 for the rest of it. Sometimes people want to go back and forth in fast forward or review mode to hear it a second time after they've written it down, if they need to write it down. So I'm gonna do that and break this into 2 pieces that are slightly smaller. Some pitchers, as they reach back and then throw the ball forward, we're saying that their arm from their farthest back position to the point where they let go of the ball, so from behind their head until they release the ball out in front of their head, that's 1.5 meters. Notice it says 100 miles an hour. Again, that's only there so we know about how fast 60 meters per second is, and we've got to use the meters per second, not the miles per hour. So that's just there to give us a kind of a real frame of reference for the numbers that you're used to. So determine the force, the net force that the arm exerts on the ball. So the mass, remember mass is in kilograms, one of the early learning target things at the beginning of this thing. So remember that mass is that. We want to find the force exerted. So I'm going to come over here to the left and say delta X is 0.15 meters. 1.5 meters. I thought 0.15 seemed a little too small. What else do we know? The final speed, V final, is 60. V initial, they reach back and they reverse their motion to bring the ball forward. So at some point, the forward and backward motion is 0. And so the initial velocity we'll say is 0. And the exit point for when it leaves his hand is 60. And is that about all we know? Well, it looks like that's all we know. So if the ball is going to get thrown to the right, then our force of the hand, we'll call it, maybe you want to call it applied force, sometimes we call it that. There's got to be some sort of up, another force from the hand holding the thing up to counteract the gravity that's always pulling down on the ball. Those two don't really come into play here. This is kind of like the braking force for the car before, except for opposite. It's accelerating the ball instead of before stopping the car. But again, we've got all this kinematic equation stuff. So these variables are kinematic equation variables. So that should probably tell us we got to do something with kinematic equations, and it's going to be just like the car. So if we want to find the net force, if we know the mass, which we do not, we need to know that. So, oh yes, we do. I'm sorry. It's right here. I thought we did. So if we know the mass and we know the acceleration, multiply them together, and that is the net force acting on the ball. So let's find A. As soon as we know A, so 0.15 kilograms times the A is equal to how much force that pitcher's arm is putting to the ball. So use the same equation, V final minus V initial. Yes, minus this time, not like this other equation where we're doing displacement. So V final is 60, so not a negative this time. And problem, there's no time involved. Can't use this equation. But what we can use, because we don't know time, is the V final squared equals V initial squared plus 2 times A times delta X. What's unfortunate with this is it's kind of a messier algebra because of solving for A. So initial velocity was 0. I'm not even going to take a line to write that. V final is 60. And 60 gets squared. So I'm going to just kind of regroup these. So we have 2, and our delta x was 1.5 meters, and then I'm going to leave A hanging off there to the right, because we can just call this 3 if we multiply those two together, and that saves us maybe a little bit of time. So 60 times 60 is 3,600. 3,600, and then divide that by 3 to solve for A. So A is 1,200. And so if I plug that in up here, 0.15 times 1,200, we get 180 newtons. So like I said a little earlier, if me talking through this runs it a little too fast, just rewind the video and pick up pieces and parts where you need to hopefully clarify things. I will stop the video now and make a part 2 for the rest of the worksheet.